Hi everyone, my name is Hui-Ru Irene Ho, and I'm from the University of Wisconsin-Madison. I'm going to present this work, It's Not a Replacement, Enabling Parent-Robot Collaboration to Support In-Home Learning Experiences of Young Children, advised by Professor Edward Hubbard and Bilge Mutlu. Social robots have been used in various fields of education such as second language learning, reading, mathematics, and science. A lot of prior work has focused primarily on interaction dynamics between children and robots. For example, a single child and a single robot, multiple children and a single robot, or a single child and multiple robots. Overall, studies related to interactions between a robot and a child or multiple children are relatively abundant. However, more attention needs to be oriented towards including adults in these interactions, given the importance of mediating technology use for children. For example, prior work looked into how a social robot could be used as a teaching assistant to support children's learning and teachers' pedagogy in the classroom setting. For children at a younger age, they rely more significantly on their parents for learning in home environments. Existing literature from developmental psychology also suggests that active parental involvement within the home environment holds particular promise for enhancing children's learning outcomes. Therefore, in this work, we aim to focus on exploring the design space for parent-child robot interactions. More specifically, we ask the following research questions. How do parents perceive and envision their use of a social robot to facilitate a young child's learning experience? What are the design considerations for a social robot for parents to engage their young child in learning? To answer our research questions, we recruited 10 parent-child pairs, each include one parent and one child aged 3 to 5 years old. There are 4 female and 6 male kids in our sample. On average, the kids age 4.3 years old and the parents age 36.1 years old. During the study, each parent-child pair read 2 books with our prototype social robot. All sessions were audio and video recorded. Afterwards, parents were interviewed about their experience and preferences for using social robots in such learning contexts. Here's how parent-child pairs interacted with the robot. Parent-child pairs initiated prompts from the robot by scanning tags in the book. They can repeat and initiate responses from the robot by pressing the right or left bumpers. In our study procedure, parent-child pairs were first introduced with a warm-up booklet to familiarize themselves with the robot's features. They then selected a book and utilized the features while they read through the book. Here's a video of the interaction during the reading sessions. The prototype robot served as a technology probe in the study to offer live experience for parent-child pairs and foster our interviews with the parents. I'd like you to focus on how parent-child interacted with the robot, how parents react to the robot's response, and explain what mistakes the child made in her prior answer.
It's a party, a pepperoni pretzel pizza party.
The tag!
Oh my gosh, a tag! Okay, sorry. I'm going. Okay, she turned green.
Can you count the number of Pete's friends in the pool in an animal-shaped floaty?
Yeah.
1, 2, 3, 4, 5.
Oh, we have that one already. Try again. 1.
1, 2, 3, 4.
Answer.
4 of Pete's friends are in animal-shaped floaties. That looks like fun.
Okay. Squirrel said pepperoni and pretzels would be just fine, but I really love pistachios on mine. Pete and the gang were puzzled. Pistachios? Well, that's something new, but maybe pistachios could be groovy too. There's another tag.
Yeah.
Okay. Oh, she turned green.
Can you count the total number of pretzels on the pizza and table?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Hit the answer button.
There are 9 pretzels on the pizza and table.
Yeah, I think we counted this one twice.
After all the studies, we conducted thematic analysis on our qualitative data. We present three main themes that capture the notion of parent-robot collaboration. The first one is parent-robot collaboration factors. The second theme is parent-guided factors on collaboration. And the third theme is robot-guided factors on collaboration. Our first theme is parent-robot collaboration factors. In this theme, we uncovered that parents envision the robot as a collaborator instead of a replacement of their role. For example, participant 5 described how she thinks the robot was partnering with her instead of taking her place. We also identified that the collaboration patterns described by the parents can be explained by CAN factors, which we will explain in the next slide. C stands for parent-robot relative capability. A stands for parent availability, and M stands for parent motivation. For parent-robot relative capability, we found that parents intend to prefer that the party who is more proficient in doing a specific task can assume more authority and responsibility. For instance, parents could leverage the robot to supplement their limited knowledge to an extent that robot could help generate questions that the parent may not be able to come up with. In addition, parents could also use robot as a third party to validate their answers or convince their children what is correct. They also envision the robot to adapt its level of scaffolding towards the parent's capability and expect that the robot could be better at promoting children's engagement sometimes with its interactive features. These examples show that a social robot could supplement parents' limited capability in knowledge, validation, scaffolding, and engaging children. For parent availability, we found that parents prefer the robot to assume more responsibility when the parent is temporarily unavailable. For example, parents may be capable of supporting their kids but may need to take care of the other sibling or cook dinner sometimes, and therefore they wanted the robot to provide educational support when they're busy. For parent motivation, we found that parents prefer the robot to assume more responsibility when they themselves lack motivation to support their children. For example, participant 4's children really likes to play an educational game many times. While the parent was happy to play with the child, she did not want to play the game over and over again, although she hoped her child has somebody to play with. In such case, the robot could take the place of the parent to support the child by playing the game with her. Our second theme is about parent-guided factors on collaboration. In this theme, we observed that although technology provides a lot of features and support, parents are still active participants who want to ensure that their objectives for education is achieved for their kids, and that their concerns of technology use is mitigated. In terms of educational objectives, for instance, P1 wanted to make sure her child understands the process of problem solving, so she explained a lot more to her kid on top of the robot's answers. P6 expressed her wish to have explicit parental controls in terms of concerns over what her kids can see and hear, as she has concerns about the content of her kids, what her kid is exposed to. Let's take a look at what kind of educational objectives and concerns parents have for a social robot in learning contexts. For educational objectives, parents focus on intellectual development or social emotional development. In addition, a lot of parents also mention the goal of promoting children's independence, and these educational objectives help determine what parents expect the robot to do during a learning activity. For concerns about the use of robots, parents describe worries about privacy, content appropriateness, and balancing the time spent on human-robot interaction and human-human interactions. These concerns help determine the constraints the parents may impose on the robot and imply what mitigation strategies designers should integrate into a robotic system. Our third theme is about robot-guided factors on collaborations. In this theme, we found that parents expect the robot to handle changing interaction dynamics and varying preferences for interaction initiatives based on the context. In terms of dynamics, for example, P5 said that she wanted to have choices to switch between having parents involved or letting the child interact with the robot on its own. P4 expressed in terms of initiative that she wants the robot's initiatives under her control all the time and preferred not to let the robot perform any autonomous actions. Let's take a look at what kind of dynamics and initiative parents mentioned. Interaction dynamics refers to how the robot managed the number and kind of participants as well as the involvement of each party. Parents discussed three major patterns. There were situations when the parents preferred the robot to interact with the child one-on-one, for example, when they want to promote the children's independence or when they're busy. There were also situations when parents want to be part of the child-robot interactions. Either the parent or robot may lead an interaction in such case. For example, P5 mentioned that she would like to choose between being able to involve more or less. Lastly, there were also discussions around times when parents want to bond with the child one-on-one without the robot being involved. Interaction initiatives refers to how much autonomy the robot is granted to initiate an interaction. We discussed 4 different kinds of initiatives here. User-driven initiatives is when the robot is fully controlled by the users for taking any real-time actions. User-authored and robot-driven initiative is when the user predefined when they want the robot to do certain things, and the robot can initiate the actions at the scheduled time. Robot-driven and user permission refers to the situation when the robot could suggest an action on its own and the users could choose whether they want the robot to initiate the actions or not. For example, P7 mentioned that the robot could raise her hand when she wants to talk, and then they could choose whether they want to allow the robot to talk or not. Lastly, the robot-driven initiative refers to situations when the robot can creatively generate its own behavior without any limitations. P7 mentioned that she could imagine the robot roaming around and say, "Let's build a racetrack," or something similar, to help come up with creative learning opportunities in the home. Overall, we discussed 3 themes that capture the notion of parent-robot collaboration. We synthesize our finding into 3 research design implications. First, the robot's responsibility in collaboration with parents should not only align with parents' objectives, mitigate parents' concerns, but also supplement parents' limitations based on the capability, availability, and motivation framework. Second, the robot's level of involvement can be defined by the CAM factors. Designers and roboticists should consider how we can build effective models to support robotic systems to handle changing interaction dynamics. Lastly, the robot's degree of autonomy is based on different types of interaction initiatives that parents prefer in different activities or their personal concerns. Designers and roboticists should come up with effective methods to determine the preferred degree of autonomy for the robot, especially the 4 major patterns mentioned in the paper. Thank you so much for listening. Please scan the QR code to read our paper and feel free to contact us if you have any questions.